Binary codes. What are binary codes? Binary coded decimal is a way of representing decimal digits using a group of 4 binary bits. Each decimal digit, from 0 to 9, is encoded using its equivalent 4-bit binary pattern. This allows us to work with decimal numbers in digital systems while still utilizing the efficiency of binary encoding. Binary coded decimal. As we naturally live in a decimal world, we need some way of converting these decimal numbers into a binary environment that computers and digital electronic devices understand. And binary coded decimal code allows us to do that. We have seen previously that an n-bit binary code is a group of n bits that assume up to 2 n distinct combinations of ones and zeros. The advantage of the binary coded decimal system is that each decimal digit is represented by a group of 4 binary digits or bits in much the same way as hexadecimal. So for the 10 decimal digits we need a 4-bit binary code. But do not get confused, binary coded decimal is not the same as hexadecimal. Whereas a 4-bit hexadecimal number is valid up to F16 representing binary 11112, binary coded decimal numbers stop at 9 binary 10012. This means that although 16 numbers can be represented using 4 binary digits, in the BCD numbering system the 6 binary code combinations of 1010, 1011, 1100, 1101, 1110, and 1111 are classed as forbidden numbers and cannot be used. The main advantage of binary coded decimal is that it allows easy conversion between decimal and binary form. However, the disadvantage is that BCD code is wasteful as the states between 1010 and 1111 are not used. Nevertheless, binary coded decimal has many important applications, especially using digital displays. In the BCD numbering system, a decimal number is separated into 4 bits for each decimal digit within the number. Each decimal digit is represented by its weighted binary value, performing a direct translation of the number. So a 4-bit group represents each displayed decimal digit from 0000 for a 0 to 1001 for a 9. So for example, 35710 in decimal would be presented in binary coded decimal as 35710 equals 001101010111. Then we can see that BCD uses weighted codification, because the binary bit of each 4-bit group represents a given weight of the final value. In other words, the BCD is a weighted code and the weights used in binary coded decimal code are 8, 4, 2, 1. Commonly called the 8421 code as it forms the 4-bit binary representation of the relevant decimal digit. Binary power. 2 power 3, binary weight 8. 2 power 2, binary weight 4. 2 power 1, binary weight 2. 2 power 0, binary weight 1. The decimal weight of each decimal digit to the left increases by a factor of 10. In the BCD number system, the binary weight of each digit increases by a factor of 2 as shown. Then the first digit has a weight of 1 2 power 0, the second digit has a weight of 2 2 power 1, the third a weight of 4 2 power 2, the fourth a weight of 8 2 power 3. Decimal to BCD conversion. Decimal is very similar to the conversion of hexadecimal to binary. Firstly, separate the decimal number into its weighted digits and then write down the equivalent 4-bit 8421 BCD code representing each decimal digit as shown. Binary coded decimal example No. 1. Convert the following decimal numbers, 8510, 57210 and 857910 into their 8421 BCD equivalents. 8510 equals 100000101. 57210 equals 010101110010. 857910 equals 100000101111001. Note that the resulting binary number after the conversion will be a true binary translation of decimal digits. This is because the binary code translates as a true binary count. BCD to decimal conversion. The conversion from binary coded decimal to decimal is the exact opposite of the above. Simply divide the binary number into groups of 4 digits, starting with the least significant digit, and then write the decimal digit represented by each 4-bit group. Add additional zeros at the end if required to produce a complete 4-bit grouping. So for example, 11011012 would become 0011101012 or 3510 in decimal. Binary coded decimal example number 2. Convert the following binary numbers, 10012, 10102, 10001112 and 1010011100.1012 into their decimal equivalents. 10012 equals 1001 BCD equals 910. 10102 equals this will produce an error as it is decimal 1010 and not a valid BCD number. 100011112 equals 01000111 BCD equals 4710. 1010011100. 1012 equals 010100110001. 1010 BCD equals 538. 62510. The conversion of BCD to decimal or decimal to BCD is a relatively straightforward task, but we need to remember that BCD numbers are decimal numbers and not binary numbers, even though they are represented using bits. The BCD representation of a decimal number is important to understand, because microprocessor-based systems used by most people needs to be in the decimal system. However, while BCD is easy to code and decode, it is not an efficient way to store numbers. In the standard 8421 BCD encoding of decimal numbers, the number of individual data bits needed to represent a given decimal number will always be greater than the number of bits required for an equivalent binary encoding. For example, in binary a 3-digit decimal number from 0 to 999 requires only 10 bits, whereas in binary coded decimal, the same number requires a minimum of 12 bits for the same representation. Also, performing arithmetic tasks using binary coded decimal numbers can be a bit awkward since each digit cannot exceed 9. The addition of 2 decimal digits in BCD will create a possible carry bit of 1 which needs to be added to the next group of 4 bits. If the binary sum with the added carry bit is equal to or less than 9, the corresponding BCD digit is correct. But when the binary sum is greater than 9, the result is an invalid BCD digit. Therefore it is better to convert BCD numbers into pure binary, perform the required addition, and then convert them back to BCD before displaying the results. Nevertheless, the use of a BCD coding system in both microelectronics and computer systems is particularly useful in situations where the binary coded decimal is intended to be displayed on one or more 7-segment LED or LCD displays, and there are many popular integrated circuits available that are configured to give a BCD output or outputs. One common IC is the 74LS90 asynchronous counter/divider that contains independent divide by 2 and divide by 5 counters that can be used together to produce a divide by 10 decade counter with BCD outputs. Another is the 74LS390, which is a dual version of the basic 74LS90, and can also be configured to produce a BCD output. But the most commonly used BCD encoded ICs are the 74LS47 and the 74LS48 BCD to 7-segment decoder/driver, which converts a 4-bit BCD code of a counter, etc., and converts it into the required display code to drive the individual segments of a 7-segment LED display. While both ICs are functionally the same, the 74LS47 has active low outputs for driving common anode displays, while the 74LS48 has active high outputs for driving common cathode displays. We have seen here that binary coded decimal or BCD is simply the 4-bit binary code representation of a decimal digit with each decimal digit replaced in the integer and fractional parts with its binary equivalent. BCD code uses 4 bits to represent the 10 decimal digits of 0 to 9. So for example, if we wanted to display decimal numbers in the range of 0 to 9, 1 digit we would need 4 data bits enable, decimal numbers in the range of 0 to 99. 2 digits we would need 8 bits 1 byte, decimal numbers in the range of 0 to 999, 3 digits we would need 12 bits, and so on. The use of a single byte 8 bits to store or display 2 BCD digits, allowing a byte to hold a BCD number in the range. If this BCD odyssey has left you captivated, show your enthusiasm by hitting that like button and sharing your thoughts in the comments below. Don't forget to subscribe for more captivating content, and make sure to ring the notification bell so you never miss a moment of our deep dives into technology. Thank you for joining us today. Until next time, keep learning, keep exploring, and keep pushing the boundaries of your knowledge.